So similar to what we did in 1-4, what I want you to do is turn the video off, and I want to see if you guys can actually answer the do now, which is the first example that's above. Like I said, pause the video, do the problem, see if you can answer it completely, and then hit play again so you can hear how I go over it. All right? All right, so let me just scratch this one out because I'm not going to do that one. All right, so we're going to do now. So it says, given the function x squared plus 2x minus 8 over x squared minus 4. So we have a lot to do here. Describe all points of discontinuity, sketch the graph, find the limit as x approaches -2 from the left and the right. So step 1, we look at our function. We say, okay, well, bottom is a difference of squares. Top is a trinomial. Okay. We have two things in the denominator that we can set equal to 0. We get -2 and we get a +2. The x minus 2 cancels. So as soon as that cancels, that becomes a removable whole. And the x plus 2 does not cancel, so that is a non-removable vertical asymptote. So you have 2 points of discontinuity. We described it. Okay. We're going to sketch the graph, and then we're going to find the limit. So we're going to find the limit as x approaches -2 from the left, and we're going to find the limit as x approaches -2 from the right. But we have to sketch it first. So we have a vertical asymptote at -2, and then at +2 we have a hole going on here. So when we plug values in to the right of -2 and to the left of -2, to the right we're going to get a positive value, so it's going to be up here. But as you approach that 2, just make sure that you leave a hole. Anything to the left of -2, when we sub it in, we're going to get a negative value. So we're going to be in quadrant 3 down here. So that is what our sketch looks like. So we described it, we sketched it, and now we're going to find the limit. So the limit as x approaches -2 from the left is going down. So that is -infinity. And the limit as x approaches 2 from the right is going up. So that is +infinity. The limit as x approaches -2 in general, it didn't ask for that, but you would say limit does not exist because it's approaching 2 different values for that particular one. Okay, so let's see. So properties of infinite limits on the bottom, and then we have a couple properties to just discuss on the back. And then that's it for chapter 1. There's one more lesson, though, that we have to incorporate with this limit stuff, which comes in chapter 3. So when we talk properties of limits here, so the same thing holds true. So we've had the sum and difference properties. We've had the product properties. We've had the quotient properties. So what you have to think about is, if we look at these two bits of information, this one right here and this one right here, f of x gives us a limit of infinity. G of x gives us a limit of 1. If you add infinity to a number, you still have infinity. If you take a number away from infinity, you still have infinity. If you multiply a number by infinity, you still have infinity. So what I'm going to do on the back of this worksheet, and again, I skipped example 1 just because it deals with something that we haven't covered yet. We'll cover it in section 3.5. But I'm going to now relate these 3 examples, or example 2, with a property that's going to be on the front, that was on the front of this page, with actually something concrete. So we're going to use property number 1 from the theorem that's on the front, and it tells us x as x, limit as x approaches 0 of 1 is 1. Well, that's a constant. And the limit as x approaches 0 of 1 over x squared is infinity. So if we use property number 1, which is our sum, then we have the limit as x approaches 0 of 1 plus 1 over x squared. So we're combining them. So the property says what we're going to do is now take the limit separately. So we have the limit of 1, and then we have the limit of 1 over x squared. So these were given. The limit of 1 is 1, and the limit of 1 over x squared is infinity. And 1 plus infinity equals infinity. Now, something to keep in mind, which I'm going to add right underneath it, but let's say we had a subtraction problem. 1 minus infinity, though, that would not be positive infinity. That would be negative infinity. Because you got to think of it like 1 minus infinity is the same thing as saying 1 plus negative infinity, and that's why it's negative infinity. All right, property number 2. So again, 2 bits of information to work with right here. This is where we have the scalar. So we have the limit as x approaches 0 of 3 cotangent of x. So the 3, you're taking the limits separately. So you can break it down like we did up here, or there's really no need. We know that the limit of the first part is still 3 because it's a constant, and the limit of the second part is going to be equal to infinity. So given that we have infinity times 3, that's still going to get us infinity. Now, if I do the other part, let's say we had 3 times negative infinity, you then say to yourself, well, would that still get me positive infinity? No. In this case, that would get me negative infinity. Property number 3, final one, this is our division. So we have the limit as x approaches 1, and it's from the left. This one should be right up here. And we have x squared plus 1 over x minus 1. You take the limit of the numerator, which is 2, limit of the denominator, which is negative infinity, and any time you have a number over infinity, that is equal to 0. A number over infinity, okay? And we're going to learn that in section 3.5, which comes next. But if we flip that, and if we did negative infinity over 2, well, negative infinity over 2, that is still negative infinity. And positive infinity over 2 would be positive infinity. So you would use these properties if you were looking at the problem and it was becoming like an addition, subtraction, multiplication, or division type of thing. Dealing, again, though, with one-sided limits, it does not have to be one-sided limits because in the A, you don't see a specific direction. But if at some point you might have to encounter these properties, if you are seeing two things being added together, subtracted, or multiplied,